So if we want to start earlier because you've got things to do, or if you want it, or if you're a little late, I mean, as long as we keep within reasonable limits, I would say that the best thing would be to be quite flexible about this. So, and that also means that if somebody, okay, because at the end of yesterday's session, there was a bit of discussion that at some point died out because everybody was knackered, everybody was exhausted. So I would take the opportunity, if anybody feels like, you know, adding something to the overall discussion on Gretl development that doesn't fit precisely within the scope of today's presentations, please let me know, and we'll see what we can do. Okay. Maybe the best thing would be, you know, writing something, you know, in the chat window, and we'll see what we can do. Okay. Having said this, let me welcome Mark Steele, whom I thank for accepting our invitation. It's very nice to have you here, especially given, okay, of course, given your stature as a top Bayesian guy, but we've had quite a lot of, you know, activity in the Gretl ecosystem in terms of Bayesian methods, and we plan to add some more. So Gretl is going, you know, from being fully frequentist orthodox place to a more contaminated place where Bayesian are not only accepted but actually encouraged to be around. So we're quite happy to have you here today. I would, yeah, as I said, we're quite flexible, so feel free to take the time you think you're going to need. And if somebody has questions, quick clarification questions, feel free to raise your hand anytime. But if you have longer questions, please wait until the end of the presentation. Thank you. So, Mark, the floor is yours.
Thank you very much. It's it's a pleasure to be here. It's a pleasure to be able to contaminate your paradigm, as you said. I'm going to try and find my slides now. One moment. If I can see where they are. That should be it. So hopefully you can see that. Yes. I'm going to try and stick to the time roughly.
Oh, sorry,
but do, you know, do push me.
Well, just one thing. Yes. I'm going to mute everybody for the moment so that we don't have extra noises, and you will have to unmute your mic yourself. Okay.
Okay. I'll try and do that.
Okay. I think we're good to go.
Okay, can you hear me now? Good. Okay, well, thank you very much for having me. As I said, it's a great pleasure. I haven't been in this particular conference before, but it certainly is very nice to explore sort of new horizons, and it's especially nice to bring you know, a message that's sort of, if you want, close to my heart. So I'm going to talk about sort of Bayesian model averaging, which is I see as a response to sort of model uncertainty, which has actually become quite a big field in statistics, because obviously people are very aware that uncertainty is an issue.
This meeting is being recorded.
Okay. And it's certainly used quite a bit, more and more, I would say, in areas of application. In economics, certainly in macroeconomics, it is becoming, I won't say the dominant paradigm, but it's certainly becoming a very important one. But also in other sciences, it actually is becoming quite an important tool, if you want. I'm going to talk a bit about methodology behind it. I'm going to try and explain it from scratch, if you want. With apologies, most of you will already be perhaps familiar with a lot of the sort of basic detail, but I'm going to try and keep it accessible. And I'm going to talk a bit about sort of key operational aspects of it. So how to actually implement it, how to make it work in practice. I'll deal with one application quite briefly, one from growth theory, from economics, which tries to answer the question, do institutions drive economic growth? There's been a fairly long-standing debate within the field, really, about whether or not this is the case. And then I'll talk a little bit about publicly available software, and of course, some of that is in Gretl. And as was noted, the presentation after this one is going to talk a lot more about what you can do within Gretl to implement BMA type solutions. And then I'll end with some recommendations and some open questions. So model uncertainty. Model uncertainty is an inherent part of modeling, as everybody of you that has actually done any empirical modeling, I'm sure is very much aware of, and especially so in the social sciences. We don't have very clearly formulated theories usually, and if you are not aware of this, or if you simply choose to ignore it, that can be actually quite dangerous. There are, of course, two main strategies for dealing with model uncertainty. Now, the classical one is that of model selection, okay, where you determine some sort of criterion which would indicate which model is the best model in some sense, and you choose that model and then conduct the inference conditionally upon the assumption that this model actually generated the data. So you forget about all the other models that you could possibly have considered, and you're basically focusing on that model. Now, this has a danger, and in particular, this will work well if the model selected is a really good approximation to the data generating process. If that is not the case, that it is almost surely going to miss important aspects of the reality that you're trying to model. And if it's not sort of systematically wrong, at least the inference is going to be too optimistic, in the sense that it's going to be overly precise, because you're essentially ignoring the fact that you're uncertain about the model, and you're doing as if you knew what the model is that actually sort of generated the data. Now, the other strategy, that is the one that this talk is sort of dedicated to, is that of model averaging, where you don't choose one model to conduct inference, but your inference is averaged over all the models in the model space that you are considering. And it's not just a simple average, it's a weighted average, and you use weights that are some indication of how good the individual models are in some sense. And these weights are either derived from Bayes' theorem, in which case you get BMA, Bayesian Model Averaging, or from sampling theoretic optimality considerations, in which case you end up with frequentist model averaging, FMA. Okay. Here I'm going to focus on BMA, if nothing else, for the fact that I like the fact that within sort of the Bayesian paradigm, it's very easy to sort of interpret the constructs that you're working with. In particular, you're dealing with posterior model probabilities, so those are simply probabilities, right? And also, in terms of computation, the Bayesian sort of version, if you want, of model averaging is often a lot easier to implement, simply because you can come up with very, let's say, because of the probability-based sort of interpretation, you can come up with very efficient MCMC schemes that actually allow you to move through model space very well and allow you to deal with huge numbers of potential models. Now, what is BMA? Well, as I said, we follow the rules of probability, really, because we're using a sort of a Bayesian setting, a Bayesian paradigm here. So the formal Bayesian response to dealing with uncertainty is to average. Okay. For example, if we want to predict unobserved, as yet unobserved observations, YF, some forecast, let's say, on the basis of a set of observations that you've observed, say Y, then you can look at the sampling model for the two sets of observables, if you want, YF and Y jointly, as this. This is just always the case, of course. You can always look at it in that way. It's just one way of partitioning that joint distribution, that joint model, into a marginal and a conditional. And here you've got the conditional for the unobserved YF given the observed Y in a given model MJ, where the parameters of the model of that particular model are called theta j. Okay, and this is for the actual observations. This is the density of the observations given that model MJ and its parameters. Okay, now then we need to, of course, because we're Bayesian, we have two things here that we need to assign priors on. We have the theta j's and the mj's. Okay, so on the parameters given the model, we're going to typically assign a continuous prior, but that doesn't really matter. But normally our parameters live in a continuous space. So so that is something that we always do in a Bayesian sort of framework. But also now for the models, for the MJs, we're going to put a discrete prior on the model space. Okay, for a Bayesian, that's a very natural thing to do because you're not sure which model to use, so you translate that uncertainty through probability. Okay, so you come up with some discrete probability measure on the model space, which could be very simple. It could simply be every model has the same probability a priori, for example. That's not perhaps a very good one to use, but it's certainly an easy one to deal with. Now, the predictive distribution is then the following construct. So this is no longer conditional upon parameters or upon models, okay, because we basically averaged out over both. Okay, so the averaging happens at two levels. There's averaging over the parameter values. So you're averaging out over the parameters because they live in a continuous space. That's an integral over the parameters with the posterior distribution of these parameters given a particular model. Okay, and that's sort of the usual Bayesian operation that you do in order to get to a predictive. So you use the information that you've got, which is Y, to get your best possible, if you want, your best possible knowledge about the parameters theta j, which is incorporated in this posterior distribution, and you use it to integrate out the parameters. Okay, so you got rid of the parameters this way. Now, in order to get rid of the models, you average over the models with, again, the best possible information that you've got, which means that you're conditioning on the actual observations to Y's. So these are the posterior model probabilities, and because it's a discrete space, you sum rather than take an integral. Okay, so that's a very straightforward extension, if you want, of the usual Bayesian procedure of integrating out over the parameters with the posterior. Now, how do you get that posterior of the parameters given the model? Well, just following Bayes' rule, of course, as usual, the posterior is just equal or proportional, if you want, to the likelihood times the prior. Okay, and this is here all conditional on a particular model. This thing here is just the integrating constant, so that this, of course, is a probability density, so it integrates out nicely to 1. Okay, now this integral you can also call simply P of Y given mj, okay, which is important for two reasons. Firstly, you use it directly, that thing, you use it directly in coming up with the posterior model probabilities, okay, because note there are no parameters here, so the parameters have already been integrated out here. So again, using Bayes' rule, that thing is proportional to the likelihood, the marginal likelihood, the likelihood of the parameters integrated out, times the prior on model space, and this is just the integrating constant, if you want, to make sure that the whole thing sums to 1, okay? And we can call this this animal here, this sum, we can call it P of Y, okay? So, so this is sort of the mechanics that underlies it, if you want, and it's just basically probability theory. There's nothing, and very simple probability theory at that. There's nothing particularly let's say, surprising about it. Now, this thing Py given m, so is the marginal likelihood, so is the likelihood for a given model integrated out with the prior, is important because you use it here. It's also important because you use it directly in, if you want, the posterior odds, or in base factors. The base factor between two models is simply the ratio of the marginal likelihoods, and the posterior odds are base factors times prior odds. Posterior odds are simply the ratio of the probabilities, the posterior probabilities of model I, let's say, versus model J. Okay. This thing here, this P of y, is this sum, and in particular, that doesn't look too hard, but the difficulty here is that this k can be huge, can be very, very large. Okay, so the difficulty is then that you have a sum over a very large number of elements here. Okay, so that's the basics. Now, of course, you don't need to focus only on predictives. You can look at any quantity of interest, let's say delta, and delta could be, for example, I don't know, the effect of education on growth, for example, which is a thing that has no that has an interpretation that is common across models. So it's, if you're doing anything in growth theory, that some models will say that thing has no effect at all. Education has no effect at all if education is not in the model, for example. Others will have varying degrees of let's say, effects that this variable education could have. And what you need to do in order to figure out what the let's say, averaged or the overall, if you want, effect is of education on growth, you'd simply take that same quantity in each model, given each model, and you average over all the models with, again, the posterior model probabilities as weights. Okay, just as we did with the predictive. So so this is becoming, as I said, a field that is rapidly growing in importance. I've got a little graph here which gives you the total number of citations to papers that have the topic model averaging in them. Okay, I got this simply from Web of Science. Over the years 1989 to 2018, and you see this is going up very, very rapidly. Okay, and these things indicate papers that have appeared either in economics or in statistics journals that had more than 250 citations at this date. And you see that a lot of these sort of important papers or influential papers in this field were published in the mid 90s to the let's say the end of the 2000s, and this is clearly sort of increasing very rapidly. And a lot of these citations now are actually in quite applied papers, because a lot of people have discovered that this is really a very good tool to use. Also helped, of course, by the availability of software that works very well. And as I said, there'll be some in Gretl that will be discussed after my talk. So what do we need? What are the building blocks that we need to sort of make this work? Well, firstly, we need to define the space of all possible models. So script M, let's say. Okay. Now, there's lots of different sources of uncertainty. You could think of three here as main ones. Firstly, what does the theory tell us about what variables are important for the phenomenon that you're modeling? And often, of course, certainly in economics, one theory does not contradict another one. Okay, so if you think that education is important for growth, that doesn't mean that capital investment is not important for growth, for example. Okay, so they could both be important, or one of them could, or none of both. So that creates lots of different models immediately. Okay. Then, of course, in terms of specification, you could have different functional forms. You could have different proxies for theoretical variables. How do you measure education, for example? There's lots of different variables that you can actually measure that you could think of as being that theoretical construct, education. And then some models will be models that have some heterogeneous aspects for different observations. Some models will be homogeneous. So there's lots of different sources of uncertainty, and the key message is that the space of models that you're actually looking at should be as broad as possible. Okay, because if you don't put a model inside the set of models that you're considering, you can't learn from it. Okay, so any model that's outside of your script M, you're essentially blind to. Okay, so you will not be able to take that into account. And size of the model space, that might be you might think that's a consideration, is really not an issue. Okay, certainly not in economics. We can easily deal with the sizes that we come across in economics and much more. So that's not an issue. The important thing is that you don't leave any models out, because if you leave them out, you will not get any information about those sort of extensions, if you want. Now, sorry. Usually, theoretical results are derived on the assumption that M, the set of all models, actually contains the true data generating model, which is called the M-closed framework. Now, in practice, we all know that that won't be the case, right? Because reality is going to be too complex in any case to be captured by any of the models that you can practically specify. So, but nevertheless, the most important results, like model selection consistency, which we'll talk about in a moment, they do extend in a very natural way to the so-called, well, M-open setting, where you're allowing for the true model to be outside of script M. Okay. Now I'm going to talk a little bit about the main, let's say, workhorse, if you want, in this field, which is also actually, for practical terms, for empirical terms, one of the most important models, certainly within economics, which is simply the normal linear model. Okay, it's a very simple model, of course, but it's one that is used quite a lot, and it's one that also we understand quite well within this BMA sort of setting. Now there, the model uncertainty will be about what covariates we use in that model. Okay, so we have a normal linear regression model where the regressors in here are the ones that will distinguish between the different models that we consider. Okay, so for example, in a model MJ, we assume that the n observations in Y are generated from this normal distribution, where we have an intercept alpha, which is common across all the models. Here we have model-specific coefficients, if you want, and covariates, and we have a common variance sigma squared. Okay, so that's the setting that I'm going to use for most of this. And we standardize the regressors by subtracting their means, which of course makes them orthogonal to the intercept, and means that the interpretation of the intercept is common to all models. We're going to assume for this that n is bigger than k, so that we have more observations, that we have potential regressors in here. We can, do without that assumption, but this is the easiest to start off with. And the design matrix, of course, has full column rank, is not singular. So the set of all models that we're considering here is the set of models that contain any possible subset of the covariates, and thus that set contains 2 to the power k models. Okay, which is quite a lot. And in economics, k can be up to 100. Certainly in growth regression, you can have up to 100 or so possible covariates that you can throw into the models. So that would mean that k can be bigger than 10 to the power 30, which is quite large. Okay, that means that you can no longer exhaustively enumerate all the models. You need to have some way of actually picking and choosing the models that are important in some sense, and we have tools for that, which I will talk about in a moment. In genetics, usually k is much larger than the number of observations that we have. the K can be simply the number of, it can be genes, for example, which genes which genes are important in a particular sort of disease pattern, for example. So it could be up to 100,000 easily, and that would give you a model space of size 10 to the power 30,000 or something, which is really, really big. Nevertheless, with other sort of efficient computational tools, we've managed to get up to sizes such as this. So it's certainly not impossible to deal with. Now, here's something about priors. Now, the prior, of course, is very important, okay? In particular, because we're dealing here not with a, let's say, a situation where we are fixing the model and just using a sort of an uninformative prior, and then the data will sort of swamp the prior. In this situation, the data does not swamp the prior, simply because a lot of this is about the marginal likelihoods, and these marginal likelihoods, they will always be sort of critically influenced, if you want, by the priors that you use. So it's very, very important that we think about the prior and that we spend quite a bit of time coming up with prior structures that are actually practical and do the kinds of things that are in line with what we want to do, that don't introduce stuff that we don't really believe in, if you want. So this is the most common prior structure. Here's the prior on model parameters, right? The prior on this, we call them theta j's in the very first or second slide or so, given a particular model. And note that this is flat on the log of sigma and on alpha. Okay, so it's an improper prior. But on these model-specific parameters, we have to be proper, otherwise our base factors would no longer be defined. And we have this construct here, which is typically called a G prior. This G is just a constant here, if you want. Note that the variance-covariance structure here is just the design matrix of the model. Okay, that is actually extremely convenient because you don't have to sort of elicit this huge variance-covariance matrix, and it leads to rather interesting properties. We just make the mean equal to 0, and the nice thing about this, even though it's an improper prior, it actually leads to a closed form for the predictive and for the marginal likelihood. Okay, so we can integrate out the likelihood with the prior or the posterior in the predictive in an analytical way, so we can just write down what that integral is. Okay, and that's very, very important for the computations, because it means that we don't have to deal with our parameters through the MCMC or whatever other numerical sort of procedure that we want. We can simply integrate them out analytically. Now, over the models, we also need to formulate a prior, and that often takes this kind of form, where we're basically assuming that covariates are included independently of each other, okay, where kj is the size of model J, if you want, and k is the number of all possible covariates, and the probability that they get included is W, okay? So that gives you this sort of very simple prior structure over the models. Which, of course, if W is 1/2, you would just get you just get a uniform prior over the models. What this requires, this prior structure requires, is only two scalars, G and W, and very often we put priors on these scalars, hyperpriors, if you want, because it's adaptive in a way, and it's certainly more robust, and I'll talk a little bit about that later. Now, what are the properties of BMA? Well, it has a number of attractive properties for popular choices of G and W. Firstly, model selection consistency. So if data have been generated by model J, then the posterior probability of MJ converges to 1 with N. So as we get more information, we're going to find out what the correct model is, if you want. And if we consider an M open setting, we're going to converge on the closest model in our model space, okay? The model that is closest in terms of Kullback-Leibler distance. BMA predicts as least as well as any single model, and there is ample empirical evidence for the fact that BMA does quite a bit better than other sort of model selection approaches. Okay, and also it leads, of course, immediately to probabilistic forecasts, and that's the kind of forecasts that end up being usually the most useful in practice. Now, how do we do this numerically? So I've already indicated that we need numerical methods to deal with this. If we only have 10 models, we can do it analytically, but not if we have more than 20 or 30, let's say, possible covariates. Then we get into the realm of a model space that's simply too large to deal with exhaustively. So we need something like a Markov chain Monte Carlo method. But as I've already stressed, the parameters are integrated out with the prior analytically, so we only have to do them on model space. So that makes life a lot easier. And the thing that people tend to use a lot is called MC cubed. I think it stands for Markov chain Monte Carlo model composition. And it's essentially a random walk metropolis Hastings algorithm, which suggests proposals around the current model, usually one covariate in or one covariate out with respect to the current model, and accepts with a certain probability to make sure that the draws are indeed draws from the correct posterior. Okay. It is implemented in freely available software. I'll talk about that in a moment, and has been shown to work very well indeed. And if you have these rather challenging cases, if you've got, let's say, a number of potential covariates which is much larger than 100, then you might need something a bit smarter, and so-called adaptive samplers, which are MCMC samplers if you want, but there you sort of tune the sampler, you tune in particular the proposal distribution as the chain is being generated. That is actually a good idea in this sense, in this case, and has been shown to work quite well for very large K. Okay, as I said, we've done in genetics, we've done work with 80 or 90,000 genes, and things do. Well, of course, it takes possibly a day or so to actually let it run, but it is quite precise, and you do end up picking the models that are the important ones. So there's no need to avoid using a large model space. There are numerical methods that actually work quite well, and certainly if within the realm of economics, you can do that on a PC in well, pretty much no time really. Now, a word about the role of the prior. So as I said, the prior is important here because it is typically much more influential than what you would expect if you're thinking about posterior inference given a model. Okay, here we're talking about ratios of models, if you want, base factors, and it becomes really much more critical what your prior is. Now, if you look at the posterior odds between models, given W and G, just in our linear sort of regression example, that actually has this very simple sort of analytical expression. Here we have three factors which have slightly sort of different sort of interpretations. So this one is a model size penalty, which is induced by the prior on model space. This one is a model size penalty, which comes from the marginal likelihood. And this is a penalty for lack of fit, which comes from the marginal likelihood. Okay. And if you look at that, here we've sort of conditioned on G and W, so we could either choose values for them, or we can put a hyperprior on them. And if you put a hyperprior on G and W, that can actually have quite a large effect on how this behaves. What are the induced penalties for model complexity? Not so much for this relative fit bit, but certainly for the model complexity. In order to show that, here is a little graph that shows you the posterior odds, okay, in a context with 41 potential regressors, 72 observations. This is the log of the posterior odds of M I versus mj. This is as a function of kj. Okay, a ki is 10, and you're assuming that the models have equal fit, so it's only about model complexity. And here you've got 3 lines. Well, you've got 6 lines really, but you have sort of bold ones and sort of lighter ones if you want. The 3 sort of different lines that you have in each group correspond to different prior mean model sizes. So you can have a prior mean model size of 7, which is this sort of solid line here, k over 2, which is here 20 and a half, which is this dashed one, and then this sort of dotted one is 2 times k over 3. Okay. Now, what's notable is that these lines correspond to random w and g, and you see that actually they behave rather differently. And this is in logs. So these are rather large differences. Okay, 150 or something slightly less than 0 is very, very different in logs.
Sorry, can I ask a question?
The hyperprice, yes, you can.
Just a small one. So is this still the case where you, a couple of slides back, you said, okay, as a simple prior for the model space, you're assuming that each covariate is introduced independently from the other. That still yes. Holds here. Okay.
Yes.
Thanks.
Yes. The only thing that's this W that appeared in that particular expression, which was the prior inclusion probability, if you want. Here it's a random, and here it is right. It's fixed. Okay. Mm-hmm. So clearly, one thing that you see is that for this random W and G, the difference between these different choices of M, different choices of prior mean model size, are much less than is the case for these fixed ones. They are also sort of less extreme here. The range of values of these log posterior odds is not so huge. And what's important is that you've got this so-called multiplicity penalty. So here you're sort of penalizing models with a size kj around k over 2, so around 20 and a half, if you want. So these models are penalized. And the reason for that is that because there are so many of these models, okay? So generally, this is felt to be a really good property of statistical procedures, that if you have huge numbers of models that are, of the same size, then you should penalize models of that size somewhat, okay? And that's what's being done here. Now, a little word on approximations. It is not always the case, of course, that these marginal likelihoods are available in closed form. If you have a different prior, it might not be the case. If you've got a different sampling model, say a GLM, generalized linear model, rather than a normal linear model, or a student T or something, you wouldn't get that. And then formally, you would have to include the model parameters into your MCMC. Okay. But that might be a really big thing to do. Okay, that should be a lot less efficient than what we've just sort of talked about. So what people then do is that, because in regular models, BIC, the Bayesian information criteria, tends to log base factor with n. So as n becomes large, the log base factor sort of converges to the same thing as BIC. So BIC is often used as an easy approximation in more complex settings. So when you have GLMs, for example, or models with endogenous regressors or what have you. Okay. There's also a tradition that is a bit ad hoc, if you want, but it does work in many situations, that use hybrids of frequentist and Bayesian methods. Okay. In the particular example of endogenous regressors, people have said, okay, let's use BIC approximations to posterior model probabilities, and let's simply average over the classical two-stage least squares estimates. Okay, and that is an approach that does seem to work reasonably well. Now, I mentioned other sampling models. Well, there are many other models that have been considered. GLMs, generalized linear models, models with outliers, student T models, dynamic models, models with endogenous regressors, models for spatial data, duration models, etc., etc. Okay, none of these probably have been researched quite to the same extent as the normal linear model or linear normal model, but they are all have been sort of subjected to some scrutiny in this sort of BMA setting. Now, I'm going to talk a little bit about the endogeneity issue, okay, because certainly in economics, that's something that does appear quite frequently in sort of practical applications. And it occurs, as I'm sure you all know, if one of more of the covariates is correlated with the error term. So we had, formerly we had just a single equation like this, or a linear normal model, if you want, where we had a normal distribution for this epsilon. Now, if we have one of the regressors, let's say x, that is correlated with epsilon, we have a bit of a problem, because we know that OLS is no longer unbiased, okay? And we use something like 2SLS. Now, 2SLS is based on something like this, adding this second equation here, where we express this x as a linear function of some instruments, W. These instruments are independent of epsilon, and then it depends on whether or not nu, this error term, is correlated with epsilon. So if nu is not correlated with epsilon, it's not a problem, of course. We don't have endogeneity. But if it is, then that induces a correlation between x and epsilon. Okay, so that's the sort of basic setting of endogeneity, and that is something which has been looked at in this context of BMA, and we found simply by simulation, if you want, that posterior inference on both on coefficients and on model probabilities is very much affected when you have endogeneity, and it doesn't go away when n becomes large, when you have lots of observations. Okay, so a number of people have tried to come up with solutions. This is what I've already mentioned before, averaging 2SLS model-specific estimates with BICB-based weights. This is a little bit more sophisticated, where they also account for model uncertainty in the instrument stage, in the instrument selection. So they propose a two-step procedure. First averages over the first stage models for the endogenous variables, so instrument equation, if you want, and then given the fitted endogenous regressors from the first stage, again takes averages in the second stage, based on approximations through BIC weights. And of course, it's not fully kosher, if you want, in the sense that you're still, when you fit these endogenous regressors by their sort of by the second stage equation, then you sort of assuming that that's what it is, and you're sort of forgetting about the uncertainty that's associated with that. Okay, there is actually a better way to do this, a fully Bayesian way. It's called so-called IVBMA, which is actually implemented in our package, interestingly enough, and it uses conditional Bayes factors to account for model uncertainty in both sort of the first and the second stage, if you want, within a Gibbs algorithm. And well, you have to do it. Everything has to be normal and whatnot, but it is a rather nice approach, which at least is exact. You're not dealing with approximations here. So so I'm gonna give you a little example now, which is an example from economics, using sort of a solution which deals with endogeneity. So now in economics, in economic growth theory, if you want, there are three main groups of theories, if you want, about the drivers of economic growth. First one is geography, which includes natural and human resources, so it includes things like education and whatnot. International trade, which is linked with market integration, and institutions. Okay, and very often property rights and the rule of law are things that are used in that context as being particularly important. Now, there's been a sort of a long-standing debate in that, and partly is because, of course, there are many ways in which you can measure these things, in which you can translate these theoretical determinants into actually variables that you can measure and that you can use in an empirical model. Okay, so there's a huge number of possibilities, a large collection of possible models that you can come up with. And to complicate matters, only geography can be safely assumed to be exogenous. And even for some things in that category, you could still argue, education, for example, is probably not exogenous. But things like whether a country has natural ports or whatever that is, that of course is exogenous. In the previous literature, there are some studies, and there's been quite a lot of debate actually about this. Some studies found evidence that property rights are a strong driver for growth. Okay, so that's in the institution category, if you want. But these studies have actually considered not that many alternative models. Okay, just a couple of models, and then they basically said, oh well, this seems to fit best, and there we are. And we now think that property rights are really important. And then there were others, of course, who had their own favorite pet theory and thought that trade should really be important. And they, of course, did the same thing. They ran some studies looking particularly at models with trade variables in them. And they didn't look too much for institutions because they believed perhaps that these were not important variables. And they came up with rather contradictory conclusions. Okay, there's been quite a lot of debate. And then there was a paper by Roderick et al. In 2004, where they tried to provide a horse race, they called it, among alternative theories and theories both for regressors and candidate instruments. But they have like maybe 30 different models, okay, and they try to cover the sort of the main aspects of these earlier studies, but they don't use BMA, okay, and their conclusion is that only institutions matter. Okay. So that is of course not really the end of it, because what happens is that it's always quite subjective in a way as to how which particular models you're actually going to be looking at, and how you look at them as well. So what people have done, and this is a paper by Lenkowski et al. In Econometric Reviews, they have looked at this, and they, for example, if you look at rule of law, which is one of these, if you want, institution variables, and integration, which is a trade variable, you can see that in this horse race paper, if you look at only those models in that particular paper, and you do a BMA type analysis on it, you indeed are left with the conclusion that these are posterior inclusion probabilities, PIPs. You're left with the result that indeed this sort of trade variable is not that important. And then if you throw in a few more models, so you have a bigger model space but still limited, you find that it's even less. Okay. However, only when you look at a full model space and do BMA over a space of all possible models that you can think of in this context, do you find that this trade variable actually comes in a quite important manner. Okay. So what has happened that in the previous sort of settings, because the model space was simply too small, you missed important aspects of the data. Okay. And you find these aspects of the data only when you look at all possible models. Okay. So and what these people found, Lenkowski et al., was basically that integration becomes an important driver when you increase the model space, and all three theories actually are supported in the BMA results using all available variables. Then a very quick word about software. There's a number of free R packages: BMS, BS, BaseVar, Cell, IVBMA, the one for endogenous regressors that I mentioned earlier. Packages for the standard normal linear model all tend to be quite efficient and accurate. And you can, if you run this for 10-20 minutes on a simple PC, then basically you've got a really good idea where you are typically. If you have got up to 100 or so covariates. Okay, so that's quite encouraging in a way. And this is all using, they all use MCMC, these packages. There's some useful resources available online. This is the website for BMS, which is very good. It's got some introductory material as well. And then Marcin and Jacek present some packages in these two papers that implement BMA, including jointness measures and Bayes in Gretl. Now, Bayes I haven't really talked about, but that basically is BMA with a particular implicit choice of G. And jointness has to do with how variables appear together in the models that end up being important. Okay, whether they are sort of substitutes or complements in a way. So that's all I wanted to say, except for the conclusions. So firstly, I hold that I believe that model uncertainty is very much a pervasive problem in applications. You can, whenever you do applications, you're going to be faced with it. Ignoring the problem is obviously not a solution. You will get biased inference. You will get inference that's too tight, too confident. BMA presents a formal solution, but of course, the priors that you use matter for BMA, and you need to be aware of this. Okay, that's why we spend so much time looking at the prior structures and seeing what their effect is. So that needs to be understood, needs to be properly communicated. And also, we found that if you use sort of robust priors by putting hyperpriors in, for example, W and G, the effect of let's say fairly arbitrary choices that you can use in elicitation is reduced, and it's generally a good idea. In terms of elicitation, try and use intuitive quantities, things like prior mean model size, things that have a sort of an interpretation for the user. There's lots of unexplored areas still. As I said, the normal linear model is quite well understood now, but there's lots of other models that people are sort of busily trying to find prior structures for that work well, understanding what the properties are, coming up with computational schemes that are efficient. And BMA, in my view, it can become a very important methodology in many areas of application, and arguably it already is in some. And I think it can contribute very much to constructive communication. It can make people better understand what the results are that your fellow researcher has found. Because if you find one thing and your fellow researcher finds another thing and dealing with pretty much the same problem, then often when you put things in a BMA setting and you make a model space that's big enough to encompass both all the models that you've considered and all the models that your fellow researcher is considering, then you can typically understand why it is that your results are different from the results that the others have found. Okay. So that's all I had. Here are some references, and I'm open to any questions that you might have. Sorry if I've ran a little bit longer than I wanted to, but hopefully it's
okay. It's okay. Thank you. It was very interesting. Anybody has questions from the floor? Okay. I can see Luca has one. I see one raised hand, and on Jacek as well. So, okay. And if there is time, I have a couple too. So I would suggest let's start with Jacek.
Okay, thank you very much for this very interesting presentation. I have a very simple question because I'm just wondering about the limitation of BMA, because we can see that the BMA train runs faster and faster, and it works well and works fantastic, for example, for the linear models. But I'm not just pretty sure about the nonlinear models, or maybe some technical issues related to Monte Carlo integration. So maybe this is a good point to discuss about also the future, because about the BMA, about the BMA.
Well, it's a good question.
Sorry, Mark.
Sorry.
Would you like to answer the questions one at a time, or do you want just to go batch at the end? What do you prefer?
I think one at a time. Otherwise, I'll simply forget what the questions
Okay,
are.
all right.
So one at a time is better for me. So yeah, no, it's a good point. I think in principle, the idea of BMA is not dependent on any given model. I mean, you can basically do that for any model setting that you want. And people have been making inroads, certainly in GLMs, generalized linear models, which are arguably they're pretty close if you want to linear models. They're of course a bit more flexible. That's where I think you sort of see, and it's encouraging because you see sort of the same kinds of issues coming through, the same types of prior structures that work well for the normal linear model. Their extensions, if you want, to the GLM, to the generalized linear model, tend to work reasonably well as well. But of course, you're quite right. I mean, it certainly is a bit of a challenge, and it can be a computational challenge, or it can be a challenge in finding prior structures that work well and that people find relatively easy to elicit. It's not clear at this moment whether it will continue to be easy or relatively easy to extend, if you want, BMA to different settings. I believe, because as an idea, as a sort of a general sort of framework for dealing with uncertainty, with model uncertainty, it's not really dependent on any given model. It's just the empirical application, if you want, or the implementation numerically that actually may become harder. But still, the fact that we can do something for the normal linear model is rather nice, because it is still the model that's used most, I think, in economics, certainly in applied research. But yeah, it's a good question. I don't really have a proper answer to it, except that I would expect that a lot of the intuition that we've got from the normal linear model will continue to carry over to other settings, and we will slowly start to understand better, what prior structures and what computational sort of algorithms we can use in these more complex settings. Okay, certainly GLMs and endogenous sort of regressors, that's looking relatively under control, in the sense that, of course, we will always try and come up with better and better ways of doing it, but it looks like this is providing very useful, if you want, answers in sort of applied questions using these models. Is that enough of an answer, Jacek? Sorry, I can't be more definite.
Of course, because this is a very vague question, yes, because we have a different type of the models, for example, and for example, we can also mention the financial models, and the complete situation is more complex and quite different, yes. So I'm just, in my opinion, or in my experience, it's just quite easy to focus, for example, in the same models of the same class, and just looking or just browsing the same among the same class of models, and some kind of determinants. Yes, it is quite straightforward. Yes, the problem is when we have different models with different explanation power, and then sometimes it's really hard to mix them.
Okay.
Okay, then we have Luca, and then we've got Alan.
Can I go?
Yeah.
First of all, thank you for your presentation. I have more a curiosity than a proper question. Recently, I've read a paper from by Francis Diebold about model combination for forecasting. And at some point, he mentioned that in the empirical literature, there is a sort of course that is, if you use model averaging with equal and uniform weights for forecast for the prediction, you have better performances, for example, than using proper weights such as posteriors. So these things puzzle me a bit, and so I would like to ask your opinion about it.
Yes, it's some people refer to that as the forecast puzzle. I think it's a little bit of a difficult issue to understand. I mean, I don't have a very clear view on it, except that perhaps the so firstly, this I think tends to be about point forecasts rather than probabilistic forecasts, if I'm not mistaken. So it's not 100% clear, you know, what would happen if you look at probability forecasting. But secondly, it may well be that the mechanics and the extra input, if you want, that you need in order to come up with properly sort of motivated weights rather than just uniform weights, could cost more than it actually gives you. I have no idea. It certainly is not the case for the sort of the kinds of sort of the kinds of problems that I'm dealing with within, or that people have been dealing with, that are typically dealt with through BMA, because one thing that you couldn't really, I mean, if you want to apply that idea, you would need a context where the number of models is actually quite limited, and you can actually completely enumerate the models that you've got, right? If you want to give them all equal weights, you have to calculate all the, you know, do your calculations or your forecasts or whatever it is with all the models that you have in your model set, in your model space. And that, of course, rules out quite a lot of the applications that we've been looking at in growth theory, because the number of models that you've got is so large that you couldn't possibly do that. So it's interesting. I really don't know. I don't have a clear view on this. It's something which is indeed a bit puzzling, but it is admittedly a slightly different context where you're looking at point forecasts and you're looking at a limited set of models, as far as I can tell.
Okay.
Does that answer your question a bit?
Yeah, thank you.
Okay, we've got Alan and then Arthur.
I have what I think is a simple question. You've explained that there's a kind of standard method for dealing with inclusion or exclusion of certain variables in choice of model, but in the context of the linear model. And I'm wondering, in the context of the linear model, or of a model that is linear in the parameters, we might be quite interested in, well, what's the functional form though? Is it squares, logs, levels, reciprocals, interactions? You know, it seems that can often make a big difference. Is there a kind of standard approach to handling that alongside simply what gets included?
Well, I mean, you could simply include that in your model space, right? I mean, you could have models that are formulated with you know, any transformation of the variables that you want, and plug them all, bang them all in your model space, and basically you're going to get answers about which models are going to be favored by the data. If you see what I mean. Sorry, maybe that wasn't your question, but
no, that's very clear. Yes, you just multiply up the model space.
Yeah.
Okay.
Okay. Then we've got Arthur and then Martin.
Yeah, thank you very much for the insightful presentation. One question, or I have the following question: is there any relationship in the research already going on, trying to, let's call it combine findings from the machine learning field, something like shrinkage and selection estimators such as Lasso and Friends, or some boosting algorithms? Because I mean, the goal there is also to select, let's say, the relevant variables out of a big pool, right? And maybe if you could say something on this, that would be interesting for me at least.
yes, I mean, yes, I mean, there is definitely, okay, I know at least well, one or two papers where people have tried to compare, if you want, machine learning algorithms with the let's say BMA produced, if you want, things like forecasts, for example. It's a little bit of a different setting in that, of course, in machine learning, models don't really have a clear interpretation, right? They are there to sort of basically, explain the data, but they don't have a clear interpretation. Whereas in what I tend to work with, or what I've been talking about, any given model that you use is still a model that at least you can sort of interpret. And I think that may be one of the main differences. If it's about forecasting or things that don't really require your models to have a particular interpretation attached to them, then I think these machine learning algorithms are actually very competitive and could even beat BMA-based sort of algorithms. Okay. So I think it is a little bit of a different focus, if you want, right?
So is it something like
that's my
sorry.
Yeah.
Is it something like data mining versus theory-driven elaboration or exploration? Yeah. Okay. Yeah, interesting.
Yes.
Thank you.
Yes. Okay.
Okay. Now we've got a question from Martin, and then I think we should have a short break.
Sorry, could you run that by me again? I didn't quite catch it.
The sound wasn't very good, Martin. Could you repeat that?
No, but I'm interested to hear the question. It's just I couldn't understand it. That's all.
I think he said elicitation of the prior somehow versus MCMC stuff, if that makes sense.
Oh, okay. Well, yeah, I think both are big, if you want, big challenges. If obviously both are problems that you encountered, and both are solved, if you want, certainly in the linear normal model, in different ways, but they're solved quite easily in some sense, right? I mean, using that particular prior structure that I've explained, you deal with the integral, if you want, that you need to deal with within that sort of within the Bayesian sort of framework in order to get the marginal likelihoods, and you only need to deal with the model space. So they are linked, if you want. So if you have a prior structure that doesn't allow you to do that integration numerically, then of course you can go to approximations through BIC, for example, but you never know how good these approximations are. So if you want to be a purist, then really you would need to deal with the parameters through your numerical procedure as well, and that's going to be really hard, because even the kinds of MCMC methods that we're using, they work very well in model space, but of course you don't need to do anything like changing dimensions, for example. If you also have to do an MCMC over the parameters within each model, then you need to come up with some sort of maybe a reversible jump MCMC or something, which is really a lot harder to implement than the simple sort of Metropolis Hastings type approaches that we can use in model space. So I think the two are linked, if you want, and I think ideally you'd always want something where you have, irrespective of the setup that you've got a prior structure that allows you to ideally get analytical marginal likelihoods, or a very good approximation, right? That you can write down analytically. And once you have that, it's you know, the numerical procedure will become relatively straightforward. As I said, you can deal with bigger and bigger model spaces, but then it becomes a matter of having a more sophisticated MC algorithm, perhaps, rather than the very simple MC cubed. So I'm not sure whether I'm not sure whether I understood your question. B, I'm not sure whether I answered it, but anyway, that's what I can come up with at the moment.
Okay, I see another raised hand by Luis. If it's a very quick one, please go, but then we have to wrap up, I'm afraid.
Yes, it's a very short question. I'm not myself a Bayesian, so I would like to know, in forecast combinations, you sometimes choose the models depending on the forecast horizon. I mean that in Bayesian could be the same or not.
Sorry, again, I'm having trouble. Could you repeat it, please?
Yes, I'm not say, myself a Bayesian, but in forecast combination, sometimes you have the models depends on the forecast horizon. So sometimes some models are good for long horizons, some are for short. I don't know, since you here choose the models, not the forecast, is that an issue here or not?
Yes, you would. I mean, you would. I mean, you can definitely conduct a BMA analysis for forecasting if you want, and you would indeed end up with choosing different models. You have dynamic versions of BMA if you want, dynamic model averaging. You could indeed choose different versions, different models if you want, if your forecast horizons are different. Because in a way that means that you're interested in something else, right? You're interested in, say, medium-term predictions rather than long-term predictions or what have you. So yes, you would. The forecast horizon is important, and you would have to specify that in advance. You couldn't necessarily use the same model weights if you want for short-term forecasts as you would do for medium or long-term forecasts. Does that answer your question?
Yes, thank you.
Okay, thank you.
Okay, so thank you. We're running a little late, but that was to be expected given the amount of interest that your talk, Mark, has raised. So thank you for your very nice survey of BMA. That's I'm sure that everybody enjoyed it a lot. So I would suggest that at this point we should have the 3 small talks about the BMA packages already present in Gretl, but I wonder if maybe we could have a short 5-minute break. Would that be okay for everybody?
Very good.
All right. Okay. So it's now 15:14. So I'll see you at 20. Okay.
Good.
Okay. 5-minute break.
The recording has stopped.